Scatter plots and correlation. Let's learn how to visualize and quantify the relationship between two variables. When we have two quantitative variables, the first thing we should do is make a scatter plot. A scatter plot lets us see the relationship between an explanatory variable x and a response variable y. We look for the direction of the trend, whether the points cluster tightly around a line, and whether there are any outliers or unusual patterns. Here is a classic dataset from Dahl, 1955. It compares per capita cigarette consumption in 1930 with lung cancer mortality rates 20 years later across 11 countries. Each dot is one country. Notice the United States in the upper right with the highest cigarette consumption. We can see an upward trend. Countries with more cigarettes had higher lung cancer rates. Let's fit a trend line through these points. The data clearly trends upward, suggesting a positive association. To quantify the linear relationship, we use the correlation coefficient R. The formula multiplies the z-scores of x and y for each data point and averages them. The result is always between -1 and +1. A positive R means the variables increase together. A negative R means one goes up while the other goes down. And the closer R is to 1 or -1, the stronger the linear relationship. Let's see what different correlation values look like. When R is close to +1, the points form a tight upward band. When R is around 0.4, there's a loose upward trend. When R is near 0, the points form a random cloud. And when R is close to -1, the points fall tightly along a downward slope. The square of the correlation coefficient, R squared, is called the coefficient of determination. It tells us the proportion of variance in y that is explained by x, for example. If R equals 0.737, then R squared equals 0.54. This means 54% of the variation in lung cancer rates is mathematically explained by cigarette consumption. The remaining 46% is unexplained. Before we move on, two critical cautions. First, correlation measures only linear relationships. A strong curved pattern can yield R equals 0. Second, and most importantly, correlation does not imply causation. In the 1850s, cholera mortality was strongly correlated with elevation, with R equal to -0.987, but the real cause was a lurking variable, proximity to polluted water sources. Lower elevations were closer to contaminated water. Always ask, is there a lurking variable? Let's recap. Scatter plots show us the form, direction, and strength of a relationship. The correlation coefficient R puts a number on that linear association, ranging from -1 to +1. R squared tells us the fraction of variance explained. And always remember, watch out for outliers, lurking variables, and the fundamental rule that correlation does not imply causation.